see. So meanwhile, I'm still seeing other people trying to enter, so I have to click a few times. I will have to change this in the near future. And sorry for this delay. I think it should work now. So I have the following idea for this current session, that I would like to tell you essentially how I'm working, what kind of material we have, and so it's not really starting the mathematics, but rather indicating to you what the circumstances are or so. I have to share the screen, and yeah, let me see which one I should use first. Yeah, I understand that maybe I'm talking just on this, that and I put it into the chat, that everybody has seen the link which is called ETH20. So ETH20, which I put into the chat. This is the link where I try to collect all the relevant information. I've updated it last night because only then I was getting access to this platform several times. So I suggest not to print it, or maybe print it once in a while. But whenever I have new information that could be new JPEG images, new code, and new hints for the lecture notes, you will find it there. I think the other most important single thing which you can get from there is the access to my lecture notes. And this is actually via a page which I call Database and Tools. If I go there, it looks like this. So I hope you have now this page, which you can enter from my personal homepage, and you see a lot of things. For you, the relevant things are the first one, which I will explain later, the BibTeX collection, which is a huge collection of papers where all of our papers are found, but mostly the one which I call script, or you could say lecture notes. In these lecture notes, maybe I make it a little bit smaller. In these lecture notes, you have various notes, and the most interesting ones for you are the following ones. The first line is course notes, which will probably increase very much during this course. The title is coming from the German Angewandte Analysis, so it's applied analysis. So it's a completely new approach to Fourier analysis, convolution, and so. And we will start with the content from this at next Thursday or so, 2 days from now. I would say that a course on signal processing is dealing with continuous and discrete signals, which are periodic and non-periodic, and especially the standard Euclidean setting. So you would say continuous non-periodic signals or functions of time are dealing with infinite dimensional function spaces. So you have signals, and it's very easy. If you give me any number like 10,000, I can produce 20,000 linear independent signals just by putting them into different intervals, for example, and they will be independent because they are orthogonal in the Hilbert space, if you want to see it in this way. So we will regularly come back to facts from functional analysis. And for me, functional analysis is just the theory of vector spaces without using a finite dimensional basis. So you see the next course is material on linear algebra. I have given linear algebra several times, and I must say I've started to like it. It was an old-fashioned topic when I was younger, and now it's in the center of so many applications, and it has become much more useful, and it is kind of practically doable using MATLAB and other software packages. So these three things are something where I may refer from time to time. You can download it, but again, especially the first one will change over time. It will get more chapters. I think the first part is quite stable, and so on. Another thing which might be interesting is this Matcha 11. This was a course prepared, a 1-week course with MATLAB in Marburg. So it's applied and computational harmonic analysis. So it shows a lot about MATLAB and how I'm using it. And other things like the Canterbury notes, which were a 1-month course in New Zealand. But I have to go back to this, and I will tell you whenever this is relevant. So, of course, in order to download, you just click on this. I don't have to do this now. The second resource is I will use a lot, or the other resources are, I will use a lot software, and because it's the standard software, I'm showing you first my window with MATLAB. So yeah, this is a new MATLAB. So you don't have to bother about this. You will get enough details in a moment, or not during the course, let's say. I'm setting up my standard setting so that I have all the variables that I would like to have ready. And now, one of the things is, one of the favorite things that I like to do is to explain many things, plot FFT of I of 17. And because I know it will be a figure which should have square, I put axis square, and then I want to display it on the screen. I hope that you all see this picture now, that it's in the same screen. If not, somebody should give me a hint and tell me. But I think you should see a nice figure with unit roots of order 17 displayed with a lot of lines connecting them. Now,
sorry.
Yes, please.
I can only see the MATLAB window. I don't see the figure.
Okay, thank you. That's what I was afraid. I will now. Now I think you should see it.
Perfect. Thank you.
Okay, thank you very much. Yeah, so this is of course a nice figure, and you may ask why. And this is something everybody can do with your own MATLAB. Probably most of you know MATLAB and how to use it, but maybe not all of you are familiar with the things that I have used here. The first thing is, and I'm going back to the command, so I have to switch back to the MATLAB window. Which one was it? By mistake, I've started several ones. Yeah, I mean, just probably I'm in a different one now, but this doesn't matter. So can you see now the plot, the MATLAB window?
Yes.
Yeah. So the command was plot FFT of I of 17. Now, in order to explain how this window gives this nice figure, which I hope everybody will remember for a long time, is FFT is the discrete Fourier transform implemented in MATLAB in the form of the fastest Fourier transform in the West. So it will be one of the crucial tools in this course, and actually the basis of a lot of digital signal processing. Now, what does it mean to apply FFT to a matrix? So I of 17 is, of course, maybe I'm just recalling that I of 3 is the unit matrix of order 3, A17 is unit matrix of order 17, means you apply the Fourier transform, the finite Fourier transform to a matrix. Now, you should not be misled by the fact that you have a two-dimensional Fourier transform which you can apply to a matrix, meaning a matrix is a collection of pixels. So when you want to do a two-dimensional Fourier transforms, there is, of course, a two-dimensional FFT. So, of course, it's not the same as, yeah, maybe I'm showing you one of my standard commands. I'm having two commands. One is FFT of I of 17, and the other would be FFT2 of I of 17. So I apply the one-dimensional and the two-dimensional Fourier transform to the same matrix. And just what it tells you is it is not the same. The comp norm routine is a very simple private routine, which just says you give me two vectors. I don't care if they are row or column vectors. I always convert them to column vectors. I say, well, maybe they are equal in terms of direction, but not in terms of size. So I compare the size, which in this case is like 1 to 1.24. And then I compare the normalized vectors. So they're completely different, and I could do it differently. So what is the FFT doing? Now, what is a plot routine doing to this? It plots one column after the other. So the FFT is a procedure which applies to each of the FFTs of this. So essentially the plot here is plotting the FFT of a unit vector, which is a pure frequency. So if you look at this, you would see something, no, I don't want to switch back. You would see that you plot constant 1 as the first column of the Fourier matrix. Then you plot the pure frequency number 1, number 2, and so on. As switching the windows is a little bit more cumbersome than expected, I don't demonstrate this here. But what you see here what you have seen in the picture, and if you study it again on your own screen, is that the lines that you have are just connecting every third, every fifth window, and so on. And you have to recall, and that's another interesting and important thing that you can learn from this figure. Row number 1 is constant, so you have 0 frequency. Row number 2, the first interesting column, is maybe I'm taking now my n equals 480 and show you what this is. And then f is FFT of I of n. So the Fourier matrix, and now I'm plotting maybe in a complex way. This is another special routine here that I'm using to plot real imaginary part in a unified way. F of, I don't know, 12. So row number this, I will show you in a moment. But before, I also want to tell you that this is a symmetric matrix. So what is the difference between the matrix F and the matrix transpose? Now we have to be careful. The Fourier matrix is clearly a complex valued function. The prime in MATLAB is not doing the transposition, but the transposition combined with conjugation. So I'm really taking the transpose matrix, which at MATLAB is the command dot prime. And if I compare it, you see it's the same size, and the error is in the order of the numerical precision, which simply means there are entries which have been computed. So in the storage and the final digits after the last, there might be a small difference, but in the numerical sense, these are really equal. Now I'm switching back to the plot that I would like to show to you. And I hope you see now red and blue. Blue in this case is The real part of column number 12, and we have seen column equals row. And what you see is clearly a pure frequency. And how many peaks do you have? Well, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. So, okay, you're in row or column number 12, but you only have 11 frequencies. But that's clearly the same effect as you start with 0. So column number 1 is 0 frequency, column number 20 is frequency 19. And as you go on, you see how these things work. And everybody who knows that rotation by 270 degrees, the same as negative rotation in the opposite direction by 90 degrees, will appreciate that this sine function is just changing the sign if you come from the negative side. So I have another command and I go back to my MATLAB window. Maybe I'm, yeah, MATLAB. I hope you can see now the same window that we've had before. Unit roots is another small command of order 4 are just +1, and you see I'm going in the mathematical positive sense, I minus 1 I. So if I plot unit roots of order 8 with red stars, that's one of the simple commands. Okay, well, I see on my screen units root of order 8, axis square, but I don't think I have to change the screen to show it to you. I will store these pictures and share the code. Yeah, maybe I go back. Maybe plot num, that would be better. That's another plot with numbers, unit roots of order 8. Yeah, now I'm changing the screen again. Now you should see, maybe I do axis off. Yeah, now you see the unit roots of order 8, and you see, maybe not all of them, but it starts with number 1, 2, 3 is at 1, so sorry, 4, 5, 6, and so on. And you see clearly the last guy has number 8, but practically speaking, it's the other neighbor of the 0 position. So you have to think that this is omega, this plus number 1 is omega to the power 0. We're talking about unit roots of order 8, which means we have 2 pi divided by 8, or 360 degree divided by 8. I'm sorry, thank you. There's some people I should let in. I hope that everybody is here. So you have, this is cosine of 45 degree plus I times sinus of 45 degree at position 2. So the elementary unit root of order 2. And if anybody is giving you a vector of length 8 and you're doing FFT or so, you should think, well, it's clearly, you have learned this probably in all the courses, it's a periodic signal. But there is a real psychological hurdle in this situation, because when you give me a vector, I would say, vector in MATLAB or so, it has coordinates, and if it's in R8 or C8 complex numbers of 8 coordinates, it has 8 coordinates. So it has a first coordinate, it has a last coordinate. I remember when I was starting MATLAB, I was really upset that they didn't allow to put an index 0. So I was thinking maybe I should store not vectors, but vectors plus indices. So we would like to say x0 is here, x2 or so is here, and so on. Then that would be x7. But I think it's much better, and the experience of many courses I have been teaching, and to think, no, it's the way how you put your vector on the unit circle. So the right way of doing it will be, if somebody is giving you a sequence of vectors, you have to think of these vectors in such a way that the value at 0 is the one at omega to the power 0. And you wrap it up in this way. So a good way, and now I'm going back to the MATLAB window, is, yeah, maybe I explain first here. When is a function on the unit circle symmetric? And symmetric, of course, means with respect to the structure of the unit circle. And it turns out this is the value at 0, so it's nothing to change. But the second coordinate and the last coordinate have to be equal. The third coordinate and coordinate number 7 have to be equal. So instead of the standard, I will go now back to, hopefully, to the window. Instead of saying, well, I'm taking x is 1 to 8, and flip left right of x is, of course, what you expect. So something which is not changing under the flip is supposed to be symmetric, but in reality, for Fourier analysis and all these things, we deal with functions on the unit circles. So we should take the involution. This command would also respect complex parts, which I try to ignore for the moment. So it's symmetric in the sense that from number 2 to number n, the coordinates are symmetric, and that there is no difference between this vector and this vector. Now, maybe I'm taking xx is x plus invol x, and you're getting this vector. Okay, it's a very primitive or so, but the main point is, maybe I'm taking this x is random. Yeah, maybe another standard command I'm using quite a lot. Random complex vector. So this is just a vector with 8 complex coordinates, and the norm of the vector is 1. So that's why I call it the random complex n. If you plot with such a vector, you will see it's in the unit square, but symmetric around 0. So it has, first of all, random amplitudes from negative to positive, real and imaginary part, and then it's normalized. Now, if you're asking me what can you say about the Fourier transform of the involutive version of this compared to the conjugate of the Fourier transform of the x, that should be 0. Sorry, something is wrong. Sorry, now I'm too sloppy. Yeah, there is a bracket missing here at the beginning. Involution, yeah, now you see. So it's really.
I'm sorry. I think we can see the wrong window. We still see like the figure on.
Thank you. Sorry. So you have not missed too much because, yeah, I was making stupid things, but now you should see it again. Maybe. Thank you. So it's just telling you, if I take either the involution on the Fourier transform side, or I take a conjugation on the Fourier transform side, or involution on the time side, that's exactly the same. So when you study the Fourier transform, you learn a function is symmetric if and only if the Fourier transform is real valued. This is a consequence of such a rule. And very often, even in some very practically oriented books, you don't find this hint that when you do the involution, you shouldn't just flip the vector in the changing the order, but you should keep the 0 invariant. Now, I'm telling you that we have a special version of the Gauss function. How we do it will be explained also later. So G is my standard Gauss function, and we have a tradition in the group that, or I have established a tradition that maybe I'm telling you what the n is. When we have code from different people, the last two initials, the last two letters very often indicate the initials of the author of this code. So it was Norbert Keiblinger in my group a long time ago, who was suggesting to use this specific version of the Gauss function of length n. Roughly speaking, you can say, if I have to create a discrete Gauss function with 480 samples, so we have to create a function which is living on the unit roots of order 480. Then you should start, well, you should start where everybody would start at 0. And 0 of the Gauss function, of course, means you take the right part of the Gauss function and you sample in an appropriate way so that you get 480 samples. And before displaying it, the switching of screens, as we see, is a little bit cumbersome. I want to tell you, is this Gauss function really having the properties of a continuous Gauss function? And as you will see, it has these properties, FFT of the Gauss function. And well, this is not exactly what you expect. The Gauss function in the continuous setting you learn is one of the very few functions, actually there are not so few, but one of the few well-known functions which are Fourier invariant. Now we see that there is a change, but let's check for in a different way. Take again a random vector of size n, maybe a row vector, and so the norm of this vector is 1, and the norm of the FFT of the same vector is 21. What is the inverse? Well, this is exactly the number that you see here. So it's not a kind of lucky incidence, but it's of course always true that the length of the Fourier transform has a square root of n. This is the way to understand it. If you once you understand it's a linear mapping going from the signal, from the vector, so to say, to the Fourier vector. If this is linear and it always changes the length by a fixed factor, I mean, if you trust that this is true, you just take the unit vector, the first unit vector, which is that will be the Dirac delta at 0, so to say. Its Fourier transform is the constant signal. So the constant signal has 1, 480 times. What is the L2 norm of this vector? Well, it's 1 squared n times, which is of course n, and then you take the square root, and that's exactly this here. This is why I like to take the routine FFT unitary. This is just Fourier transform divided by square root of n, and then you see this discrete Gauss function, which I'll show you in a moment, has the property that up to this normalizing factor, which you can never avoid, you will have exactly a function which is invariant. And you can test it for any n, and that will work fine. So I'm plotting it, and I'm maybe just don't do too many technical details, but I will plot it in our way. Plot C is plot in a centered way. We don't want to see this function plotted in a naive way with this nasty peak at the beginning, but we would like that this function looks like a function which is familiar to you as a Gauss function. So I change again the new, so now you should see this Gauss function, and it's a function now which is living on an interval from, well, probably minus 248 or something like 200, yeah, 240. And MATLAB is rescaling everything so that you see this Gauss function in this way. And the best way to explain a little bit what is in the background, if I would take n equals 144, if I take the Gauss function of size 144, I would say, well, I have to take this continuous, this will be explained in detail much again and again later on also. I would like to have something which has a period of size 12 and a sampling rate of 1/12. In this way, I would say, okay, take the Gauss function, sample it at a rate of 1/12, but use it only on the basic period, which is going from -6 to +6. So in that case, you would put new labels and you would say, well, these are the values of the continuous Gauss function at certain points. Here, I really just, in the plot that you see, you have just a discrete vector and you plot it in this way. Now I'm showing you what you would see if you would just take the same curve in the, I'm not sure if I can make it smaller. I'm not sure. I hope you can see the right end. Maybe if I move it, you see the right end. So it's, why do we have this nasty curve? Well, because the first component is the peak, that's the maximal value. And of course, also my Gauss function is normalized so that I get always a vector, a typical vector with Gaussian shape, with n components and norm equal 1 in the usual Euclidean sense. So the Euclidean norm is 1. So you have the peak value here, and then you go down in a symmetric way. The second third or so is the same as the last, the second last, and so on. That's because you think that the Gauss function should be centered around 0, which is plausible, which means it's centered at the unit roots of order n at 0, so at 1, at the on the right part of the unit roots. And now if somebody is asking you, how should you plot, how should you cut a function which is living on a circle? I think there are only two natural ideas. One idea is to cut at 0 again, and this is how the data structure in MATLAB is working. So if I would look at the values, you would see the first values are non-zero, then it decays very quickly. And then you have a lot of values which are very close to 0 or below numerical precision, and only the very last coordinates are going back and are giving the other values. Now, this is not nice for a plot, because for a plot you would like to cut it on the opposite side. I have studied a number of engineering books and can tell you, for example, there's a book of Fölz, I think it's for people doing astronomy or so. And there he says, well, the discrete Fourier transform is different from the ordinary Fourier transform because it's not true that you can do the convolution by multiplying the Fourier transform. You have to apply a shift. And that has a lot to do with the data structure. So essentially you could say, well, I would like to see a nice plot, but I'm willing to have cumbersome treating and new rules for the discrete Fourier transform compared to the continuous one. Now I'm saying, no, from a mathematical point of view, you think that the Gauss function, the continuous Gauss function, is on the additive group of real numbers. So it's living on the line and 0 is the midpoint. So the value of 0 should be put on the unit roots of order n at the neutral element of the multiplicative group of unit roots of order n. And that's exactly, of course, omega to the power 0, which is 1. So rather preserve the group theory and have a separate plotting routine. So I'm going back and say, well, for plotting purposes, I am using the data structure and I make a new vector gluing together the last end and the front end. I'm putting labels in the right way, and I have a more complicated but easy to use plotting routine. Of course, I'm willing to share these routines with you anytime. And then you have a better data structure. Okay, maybe this is a good moment. I will take a quick look if there is, I will change now the topic and so, but I will take a quick look if there is anything going on in the chat or if anybody wants to have a comment on what I have done so far, please. I think there's nothing, or at least I don't see it. Let me share a different screen, which is, yeah, maybe this one, yeah. Okay, this is GeoGebra. I must say that I have learned to like GeoGebra, I think it's GeoGebra, very much. And it's extremely easy to use. I would recommend to everybody to learn it, to download it. I'm using apparently the German version now, and it's installed, so I don't want to change it. But when you install it, you probably can. Pardon? Can you see it? At the moment, it should be an empty screen or with some code.
You see the GeoGebra.
Can you see it?
Yes.
Yeah, okay, good. What if I think of linear algebra? The way how I learned it was vector analysis. So you have row vectors, column vectors. You have this strange statement that the dual space of the space of column vectors is the space of row vectors. But if I think of a physical object like a vector in R3, I don't see how it can have a structure of a row vector or a column vector. That's why I prefer to use spaces, vector spaces, finite dimensional vector spaces for demonstrations, which are not as obviously kind of coordinate spaces. And the demonstration that I can do with GeoGebra is very easy. I say, let's take a cubic polynomials. I like cubic polynomials. Like 2 plus, and you see how I'm typing, 3x squared, it already starts, minus, 3x plus 3x minus 4x squared plus x to the power 3. So what you see here is a typical plot of a cubic polynomial, and you can see maybe I take the constant part a little bit smaller and change it just to 1, so that the 3 different zeros are easily better visible or so. Now, if I would like to see that, or maybe if I want to tell you how to shift a curve, and that's already kind of part of my notations, the translation operator. The translation operator means I have a new polynomial, q of x, which is p of, no, sorry, I want to introduce some shift parameter first. I will shift by 0 first. Okay, so I will no shift. But you see, it even allows me to make a shift in the range from -5 to 5. I can change this as well, but now I'm making a new polynomial. And as we know, the translation operator is using the same, function. So it's the polynomial that we have on the screen minus a. Now, I have to explain a little bit why we have this minus a. As we will see in a moment, if a is +1, I would like to have a shift to the right. So if, say, I shift a function by +1 and you are on the real line, you expect that it's shifted to the front end. But why do I write p of x -1 in this case? Well, the new graph, maybe I'm putting this here first. The new graph, and now I'm taking a +1. So this is the green curve, or +2. The green curve is to the right of the original black curve. And I must say, psychologically, when you see it the first time, it's the same problem as, well, we're changing from winter to summer or from summer to winter time. Do we have to move our clock forward or backward? And my explanation is, if you take the new function, in my case, the green function, compared to the black one, then it has the same values, but at different positions. If I look at the peak, which is maybe here around 1.8 or so, then I want to know where this peak occurred in the original place, and it was very much to the left by the amount, yeah, here, sorry, I should make the A a bit, maybe I make A equal 2 now, so that we have easier. So now it's 2, so the peak is now at, I don't know, 2.4, and if you look, the peak was at 0.4 originally. So the green curve takes the same values, but if you ask what is the value at a given position, you have to go back to the original position. So going back when somebody asks you for the value of a function means that the values are moved exactly in the other direction, in plus direction. So of course, if I take a minus 4, the same curve is taken and it's shifted to the left. So shifting delay operators are very important, of course, for our thing. And then you have this. So you see, this is very, very easy to deal with. Now, if you are dealing with that, the polynomial, I mean, sorry, the roots or the zero positions of these polynomials, then of course you have to look for a zero searching routine. And at the moment, at least, maybe I'm not enough familiar with GeoGebra. If you find it out, please tell it and send me a short message. But I would take the same polynomial and insert it into MATLAB. Now in MATLAB, maybe I'm switching back to MATLAB for once more. So I'm switching, no, sorry. I have to write down, or you have to recall, the coefficient sequence is 1, 3, minus 4, and plus 1. So I'm going back to my MATLAB window, and I'm showing this to you now again, hopefully. Do you see 1 to 4 now, or is it, did I activate the wrong MATLAB window?
We can see it.
Yeah, okay, very good. Okay, so the question is, how is MATLAB using the routine? So what is polyval of the vector 1, 2, 3, 4 at, don't know, at 0.7 or so? You see clearly this is the value of a polynomial with coefficients 1, 2, 3, 4 at 0.1. Now, if you're doing the same thing at 10, you're seeing a nice number. It's just 1, 2, 3, 4. So, well, what is the decimal system doing to us? It's saying, well, we look at the number, and because it has 4 digits, even a kid knows how to read this number and says it's 1,234. So this is, of course, in contradiction with the rules that we know from polynomials. In the mathematical terminology, and probably GeoGebra would accept any order, but I have used the mathematical order starting from the 0. So if we are saying now P is the polynomial described by the coefficients, then I have to write them in the opposite order. So the last term was x to the third, which is 1 times x to the third. That's the leading exponent, it's plus 1. We had minus 4x squared, we had 3x, and we had constant 1 after my change. So if you're asking what is the roots, then you will find that these are the numbers, and actually you can check them in the plot again. I don't do it, it's too cumbersome at the moment. And the roots are actually a little bit to the left and near 1.45 and near 3. So it's a typical case. A polynomial is split into these numbers. Now maybe I try to go back to this. Yeah, maybe I don't have to do it. I mean, you will trust me that if I would write x minus x1 multiplied with x minus x2 multiplied with x minus x3, so the unit, these roots of this, I would get exactly back the polynomial. And again, unfortunately, these things are not the same here anymore. I mean, I'm using MATLAB and GeoGebra alternatively. Actually, matrix analysis, eigenvalue decomposition, such things are easily done in MATLAB. Of course, I can plot a lot in MATLAB, but for some easy visualization, especially for one-dimensional signals, it's much easier to work with GeoGebra, mostly for illustration and not for number crunching or so. So I'm going back to my window with the GeoGebra. And I'm showing you a few features that are easy to learn by just watching what I'm doing. You have seen already that there is a slider. So this slider, if I move the slider, you can see it here. If I activate this, the slider is part of the image. So here you can see this is the shift parameter. If I don't like the predetermined thing, or maybe first I show you the animation. If I want to see the whole range of things, then it automatically goes through the range of parameters, which is from +5 to -5 with a particular step width. I think it's 0.1. Yeah, you can read it here on the right screen. And it goes through all the positions, so animation off. But if I want to, for example, change the color, I go to the color or so, and maybe yeah, here if I take this object anzeigen, no, Einstellungen. So Einstellungen means adjustments. For example, I can change the range only from -3 to +3, and I can ask sorry, what's happening here? I wanted to change, no, I think I have deleted it by mistake. Yeah, that was not good. A equal 0. Yeah, Einstellungen once more. Grundeinstellungen. Yeah, here. I don't know what was the error. So I want to have -3 to +3. No, I have some, I'm sorry, I don't want to play around with this now. You can change the step width, the range of the parameters, and so on. So one thing which I thought might be interesting for people in signal processing is the well-known sync function. So now I'm activating this function. I have already put it in. Maybe it would have been nice to see how I'm inserting this. Maybe I'm showing you how I was doing. Maybe I'm taking sync2 of x. That's just a new function, but let's retype it. So it's the sinus of pi, and really I say pi times x. So GeoGebra has the routine that variables have to be called x. And then you say divided by pi times x. And that's this new function, which is the red guy. And you have this function. You can display it, so make it smaller. And then you're zooming in. and you can move it around here. You can make it larger. You can move it around, you can rescale it in this direction. And also you see, if people say the sinc function is not well decaying, it's really true. The decay is like 1 over x. At these peak values, the sinus function, of course, is equal to plus or minus 1. So you have this poor decay. And if you're just doing the same trick as we did with the dilation, or a shift of the polynomial, now I'm discarding the original one and just taking this dilated Gauss function, then you can see how the effect of stretching a Gauss function occurs. So this is a very small, it's not a very small parameter. This is a large parameter. And if you stretch it, or actually you compress it, you multiply the argument with bigger and bigger periods, you're seeing a curve which has some undershoot and overshoot. And as we will see, this property of the sinc function is responsible for the Gibbs phenomenon. Is there any comment or so? Sorry for. Now, the Gauss function is done in the same way. So it is just exponential function, or e bracket minus pi x squared, and you have it, and it's plotted automatically. And again, I wanted to create the compressed function. So let's look at this here. So maybe I discard the original Gauss function. This is, yeah, maybe the range is not good here. I will try to change this again. Maybe I'm lucky this time. So the range should be, let's say, from 0.5% to 3. And you see, I don't have to click. I just go back to this. Now it's, maybe I can do animation. So what you see is a sequence of Gauss functions which have constant shape, but the argument is changing from a dilation stretched by a factor of 3. Now it's already down, now it's Gauss, and now it's more and more compressed. So this thing is, I will try to move it a little bit around. This is what we will use as a template for a so-called Dirac sequence. So you see, I mean, it's getting more and more concentrated. And the nice thing is I don't have to do anything. The machine is showing you these pictures. You can create such pictures on your own. And of course, if you would stretch more and more, you would have a more and more flat Gauss function. But what is the reasoning behind this 1 over rho? It's the reasoning that you have an area preserving thing. So the Gauss function, not my Gauss function, but the classical Gauss function has area 1. And it's clear if you compress the support by a factor of 2, like everything is kind of, every interval is getting half the size, then the height should be compensated by a factor of 2, then the area will be the same. So this is a simple application of the transformation rule. Take y equals x divided by rho and apply the standard transformation. So all the functions that you see here, down to the tiny version with rho equal 0.05 or 5%, they all have area 1. And the mystery of the Dirac function is somehow in there where you say, okay, now let's take the actual limit. And let's take that with rho equals 0. And then you get a thing which is completely concentrated at 0, but still has area 1. So this is how people are giving explanation of the Gauss function. And of course, if you think in terms of functions, this is complete nonsense, because even the most complicated, most developed theory of integration, which is the Lebesgue integration theory, would not allow, I mean, it would allow you to integrate any function, even a function having infinite values on, let's say, finitely many, countable many, or even on a set, null set. So it could be all the rational numbers in some interval that's countable. You could have the value plus infinity. So if you have plus infinity only at the value 0, in the sense of Lebesgue, that would be never giving an integral equal to 1. So some people go into mystifications and they would say, oh yes, it's kind of super infinity. It's so much infinity, much more than normal people can think of. But as we will see in the theory of distributions, it's much better to say, well, we let this kind of device, the Gauss function is a measurement device. And well, a practical measurement device tries to pick out the value of a function by integration against such a thing. And if you make it more and more narrow, it's like you have a better and better sampling device. And the Dirac is the perfect sampling. So the rule that we will see at the end is, it's not an object in the world of functions. It's an object in the world of measurements, or in the world of linear functionals, if you take the world of functional analysis or so. This is just for an intuition. It was more meant to give you an idea that maybe sometimes if you want to see what a function is doing, you just start your GeoGebra, if you have downloaded it, and you visualize some effect, and it's very easy. And it's giving you actually high quality pictures, and sometimes I will store such pictures. Now, another thing which is probably familiar to you, now I have to zoom in. Yeah, I should remove the Gauss function. And zoom in. It's a bit slow now because, but more and more you will see what's going on. Yeah. That's too much zooming. Just because it went too slow. Yeah, now it's not a very good display here, but I'm sorry for there's I have not sorry for those who have been waiting too long. I have to change this access code. Now meanwhile, the rest can take a look at this function. It's cosine of pi x squared. So if you would take the imaginary part, you would have e to the I pi x squared, which is a kind of purely imaginary Gauss function. If you look at this function, it's not a very good display. I should rescale it a little bit, but let me keep it like this. Then you would have the so-called chirp signal. Again, a very important object in signal processing, but also in abstract mathematics. And the chirp signal is something which is, if you would try to listen to a chirp signal, it would be like a whistle tone. So it's a linear increasing frequency sweep or so. So I will try to do my best to imitate it in an acoustic way. It's something like, and if you go to the internet, you will find a lot of such things where you can see and hear to these things. You can test your ears whether you still can hear, I don't know, 12 kilohertz. As we know, no human being can hear more than 20 kilohertz, which is the basis for the CD convention. Hi-Fi quality stops at 20 kilohertz. Therefore, since a sinusoidal tone of 20 kilohertz has 40,000 zeros, let's add 10% and choose the number 44,100. And that's the frequency, of course, used for the CD players. And then you would definitely not miss any acoustic information which is in an audio signal, because you're not a bat or I don't know, some animal which can hear ultrasound or so. But we'll come to the chirp signal later on. What I wanted to demonstrate is that here it's easy to type in this chirp signal. When I was originally doing, maybe I'm doing it once more, chirp 2 of X. Oh, sorry, there was a mistake. It wasn't chirp 2 is the new function of X. Should be, let's say, just cosine of X. Maybe I take a third power, which square. Yeah. No, it's still the same format. It's a problem of the formatting or so. What I wanted to say, it's not so much the chirp, but the sync function. The sync function has a singularity at x equals 0. So formally at 0, you would have sinus of 0, which is 0 divided by 0. And we all know from teaching the L'Hopital's rule that you have to take the limit x to 0. And I think it's a good feature of GeoGebra that it's kind of has built in such a smart thing. It does not display any freaky outliers or so, but is comfortable with such things. Okay, so I have already told you that the chirp signal is a linear frequency sweep, and I've mentioned some audio things. So the next thing I would like to mention to you or show to you is the gaborator. So again, I will take a short break, see if anybody wants to still enter, or I think there's nobody in the waiting room now, and whether there is anything, a comment, please kind of raise your hands or so. I don't see my chat window here, but meanwhile I prepare to open a window with the gaborator, yeah. Okay. So part of the where is it? Yeah. Do you see now the gaborator? I hope yes. Meanwhile, I can talk. Part of the course is based on ideas from time frequency analysis. And time frequency analysis is very closely related to the term spectrogram, also sliding Fourier transform, sliding window Fourier transform, or short time Fourier transform. Actually, the short time Fourier transform is the term that I will use most of the time. So it's the idea that instead of, I mean, think of a piece of music. You have 44,000 samples per second. So assume you have a 3-minute piece, and you would take the whole recording, and then you would say, I want to do Fourier analysis. Well, at the time when I was first coming to learn about the Fourier transform and so on, I knew already a lot about the theoretical mathematics of it. I was stumbling about the question, I mean, can we compute such a huge FFT, and what is the information? And I would say, yes, nowadays we can do it, but the information is irrelevant. You would see high frequencies at certain things, maybe at 44 kilohertz or so, or hertz. And then you will see, oh yes, probably it was a piece in C major. So you would get statistical information about the energy at given frequencies without any time resolution. So of course, it's much better to have a time resolution. And what everybody would do is, I mean, I can analyze sound. I can distinguish an instrument from another instrument. I can distinguish a voice from another voice by looking at the spectrogram. So even I can change my voice, and I can talk very high frequency or wide or so, and then you would be able to see quite significant changes in this. So since November 2017 about, I can point to this gaborator. So gaborator is not to be mixed up with garborator, which is what people have in the USA to get their garbage into the sink, but so in the kitchen. So it's Gabor, Danish Gabor, the Nobel Prize winner of physics for his invention of the theory of holography. But he also was an information theory person, and he was suggesting what is now called Gabor analysis. So essentially, to rebuild every signal from time frequency shifted Gauss functions. So you just take the Gauss function, shift it in time, shift it in frequency, and then you have a collection of building blocks. So that would be like tones at times. Assume my whistling is now Gauss. It's so at any time you're allowed to choose from these things. And his idea was to choose them in a particular manner with integer time shift, integer frequency shifts. And then he was hoping they would be a linear independent system, which is good enough, still good enough to represent every signal. So it's like a basis while living in the infinite dimensional space or so. And we have a whole theory, meanwhile, mathematicians started to look at this idea, published in 46 only in the early 80s. And I was lucky enough to be part of this movement in the 80s, 90s or so, and that's why I can tell you a lot about this now. But let's just say, well, this idea had a lot of interesting background, but it was not realizable in the way how Gabor was thinking of it. I mean, it's not possible to have a basis with uniquely determined coefficients in such a system, but you can still display the energy in slightly different way, slightly modified way. And in terms of visualization, I find that this gaborator is a perfect explanation, and I just play now this first piece here, and you should take a look yourself. And it takes a while, and maybe listen for a few moments. So you see the curse is aligned with the tone and the spectrogram. It's also true that it's not as simple as you may think. I mean, the pianist is hitting one key, but you see a lot of frequencies at any given moment. Maybe we stop here. So you see that there are overtones. But of course, it's the art of building a good instrument, of playing an instrument in the right way, to change the amplitude, which is the loudness, varying over the frequencies. That's the trick of, let's say, musicians playing a string or a flute or so, or in the piano of the instrument builder. And you have an attack, which is a little bit different from the long term where the sound is. You could probably read off even the melody with a lot of training. So you will see a lot of such things. And this is the spectrogram, which is, from the mathematical point of view, done properly, just in isometry from the sound signal. Well, of course, not from the acoustic sound signal, but from the recorded signal, which is, as you know, on the oscillograph, going up and down or so, into a two-dimensional picture. Actually, if you look at the lower end here, at this point here, you can even identify and say, well, what is this tone here? And it's G5, so You can even start to do transcription. You can read off, this is at 784 Hertz. And this is at, I mean, you have to point carefully, at 443. So probably this was, if you go closer, it's probably meant to be 44 Hertz. So it's the A and so on. So yeah, maybe I'm going here. It's maybe one tone above, yeah, here I'm at 44 Hertz, and it's A4. So for musicians, it's a clear way of describing. It's in the piece of music at the moment of 44 seconds from the beginning, and so on. So in the notes, I have put a link to both the Gaborator, which I think is highly instructive to tell you what this spectrogram is in terms of practice. And also a link to a talk that you can listen by the person who has written this program, Mr. Anderson. I'm in contact with him, so if you have specific questions, I might be able to ask him such questions. He's a, I would say, computer freak who has implemented this Gaborator in a very nice way with very good visualization. You can also go back and you can upload your own WAV file, which is maybe also interesting. So if you want to know how your voice is transcribed or how your instrument, your favorite instrument or favorite piece of music, just create a WAV file from it and make an upload and you will see it. Maybe I'm, meanwhile, starting this, I can still talk about this. So you have, here have a multi-instrument, and it's nice to see that guitar or such instruments have a very clear spectrum. Now you will see the drums. Now, what is also quite visible is that drums, and they are very percussive. So in the theory of signal processing, you would say this is a sequence of Diracs at equidistance. The Dirac Fourier transform is all covering all the frequencies. So if you want to know the tune of a drum, well, if it's a, I don't know the instrument in English, a pauke, so these big instruments in the classical, they are tuned, very fine tuned, so they have a clear main frequency, but the percussion that you have just heard now is going through all the frequencies. So just going back to my story, so there is a talk which I have put up in the web page for the course, which Mr. Anderson has presented, and I was very pleased to see that the spectrogram is based on mathematical investigations which have been done by some of my former students. Many of them have been active at the ARI, at the Acoustic Research Institute. And meanwhile, I'm starting the STX program, which is another thing that you can download. Let me see if it works. Yeah, okay. I think I just have to switch now to another screen. So I think you should see now a spectrogram of my current voice. Okay, sorry, Marco. So sorry for all those who have been allowed to enter only later. I will try to do it better next time. So what you see here now is a real-time spectrogram. In the lower left corner, you see, if I stop it, you see that the length of the window is, maybe I take 100 milliseconds. So that means, roughly speaking, we have at the sampling rate of 44,100, 100 milliseconds is a tenth of a second, which is something which is meaningful in a musical way, and 70% overlap. And so if I start it, you can hear the recording. This is just the primitive microphone. I don't want to switch to a better microphone now because then maybe you wouldn't hear my voice. But let me try to do some whistle tone. So you see that this is a way to display the sound information with an analysis of the frequencies. So when I do, this part in the middle is almost like a linear frequency chirp. And the interesting thing that we will see later using, not today anymore, of course, later using MATLAB is that if you take a Fourier transform, then you have more or less a rotation by 90 degrees of the spectrogram. So restarting it, I will try to do a pure tone, which is like this. Okay, what you see is, of course, a straight line. What is the Fourier transform of this? Well, you put a straight line now in a vertical position, and then you see it's like a percussive delta. So if I would be able to produce a trigonometric polynomial, which is a superposition of pure tones, then you would see a sequence of Dirac functions on the Fourier transform. And actually now we are at a good point to say, I mean, what are generalized functions? I mean, there's so much mystifications about the Dirac delta or so. And after a lot of practical work with signals, trying to illustrate them, trying to compute with them or so, my view now is, I'm just again continuing to have this. So you hear now the spectrogram of my voice. I can change my voice and make a so I'm producing strange sound, if you want. Is this a function? Is this a function in L2? As you normally say, signals are elements of L2. I mean, yes, the Hilbert space L2 is very important. We will use it all the time. But for me, one way of explaining it is, I mean, a sound signal is something that I can record and of which I can make a spectrogram. Now, if you would take a CD player and you would produce a spectrogram and you have an extremely high resolution spectrogram and you have a 3-minute recording, then you would probably see a piece like this one here, 3 minutes long, from 0 to 20 kilohertz. As it's a real signal, you could say it's symmetric. It goes from minus 20 kilohertz to plus 20 kilohertz. Okay, it's like a big poster or so. But if somebody says, well, I'm a bet, I can hear, I don't know, 50 kilohertz. I don't hear in my high overtones, then you would say, sorry, that's not enough. It's not recorded. You need an even better spectrogram and an even better thing. So essentially, the theory of generalized functions that I will propose to you during the course, and where I will tell you all the necessary things, but also give you the necessary illustrations, will be a theory saying, well, a mild distribution, that's the name that I have created for these objects, is either a linear functional on a space of test functions, which funny, I mean, it's appreciated, carries my name, it's a dual of Fichting's algebra, but it's just an object which has a bounded spectrogram. And we will mostly understand objects by looking at the spectrogram. And we will also do a little bit of image processing, so the two-dimensional version of this. So what is an image? And again, you could say, yes, it's a continuous function of two variables. But then I would say, well, is it an image if I send you my JPEG compressed version of it? And then you would say, okay, yes, it's a finite collection of coefficients, but I can show you on the screen what the image was. I mean, I'm actually transmitting to you through the Zoom device digital images. How are they stored? I mean, they are compressed images. Your computer or your device is decompressing it. So I would say at the end, an image is not this in reality, so to say, this infinite dimensional, infinite resolution, continuous function of two variables, but you could think of it as a collection of approximating it. Assume everybody in the class now takes a picture, is taking images of different resolutions, then together we would agree that this is the image of the spectrogram that we are just now discussing. And occasionally, and much more explicit, I will use the analogy to the real number system. I mean, we all know what pi is. Pi is the relationship between the diameter of a circle and the circumference. And it's a good, important insight. It doesn't depend on the radius. The relationship between diameter and circumference is always the same. We also have learned that this area of the circle is r squared times pi. So everybody knows if you double the radius, the area of the circle will be 4 times this. And you will say, yeah, I can compute it. I mean, 2r squared multiplied with pi divided by r squared with pi. Okay, pi divided by pi is, of course, 1. And then I'm saying, well, how can you invert an infinite decimal expression? So this, I'm now turning a little bit to slightly philosophical terminology, and we're using the symbol, and it's kind of, again, such a bona fide symbol. We can handle it, we can work with it, and we know how to compute with it. But can we ever write down this infinite decimal expression? So sometimes I'm saying maybe God is able to compute with infinite decimals. We are not able. We are using our pocket calculator. We are using Wolfram Alpha to compute it with maybe 4,000 digits or so. And we're saying, well, what is 1 over pi? Well, it's the multiplicative inverse to this symbol which exists in the world of real numbers, which does not exist in the world of rational numbers. So there are so many ways of approximating pi. We can take the circumference of the regular n, I don't know how to call it. This, I mean, I'm taking the plot of the unit roots of order n, and I connect all these points, and I take the length of this polygonal curve, and I take the limit. So yes, pi is the limit of a lot of approximations. You can choose decimal system, binary system, hexadecimal system, whatever. And all these things give the same number pi. So you realize, okay, this abstract object can be approximated in many, many different ways. Now, in the Western world, and I think worldwide in mathematics, we have learned to say, well, it's an infinite decimal expression. And if we avoid finite decimal expression, so if we write instead of 1, we write 0.99999 periodic, then it's even uniquely determined. So we don't have to talk about equivalence classes of Cauchy sequence or so. But to go back to the original idea, pi is some abstract object which is very nice for symbolic manipulation. Even 1 over pi, pi squared, and all these objects are well defined. But when you actually work with them, you have to choose finite dimensional or finite decimal approximations. And of course, the multiplicative inverse of a finite decimal. So let's say you take 3.14 as a primitive approximation for pi. This is 314 divided by 100. So what is the multiplicative inverse? It's 100 divided by 314. So is this giving you a 2-digit approximation to 1 over pi? And that fact is, no. You cannot say that you just invert the approximation to get the same approximation quality of the inverse or so. But you can say that if I need a good approximation of 1 over pi, let's say for 20 digits, I have to think a little bit and then take an approximation of pi itself, maybe with 30 components, then do the inverse, and then I'm sure that the first 20 digits of the number I'm receiving are good for 1 over pi. And so in this spirit, I would say generalized functions are objects which can be approximated by things that I have under control. And if I'm smart, I'm using, for example, finite decimal expressions or nice rational numbers, because I know how to invert a rational number. And I will try to teach you that the Fourier transform is very similar for decent functions like the Schwartz functions or other functions. You can compute the Fourier transform with the good old Riemann integral. If they are smooth enough in a very mild sense and decaying, then that Fourier transform will be of the same quality. So you can apply the inverse Fourier transform, and you don't have to learn Lebesgue integration theory, which is a great thing, but I will do the course without Lebesgue integration theory, without the theory of Schwartz, these temporal distributions, and you will see that you're not losing very much. So again, you will get in this course a theory of generalized functions, which is based on relatively elementary things. I hope to illustrate a lot of things on and off with MATLAB or with GeoGebra, or sometimes if I show spectrograms with this STX program, which you can download from the ARI site or with the Gaborator. But essentially, I would now make an informal definition or so. A 1D signal, an audio signal, is something which has a spectrogram. And again, do you think that you could ever sample my voice at infinite resolution? I mean, you can take a recording, and if it's high quality, you have 44,100 samples. If you're producing a CD, the producers sample at even higher rate, so they can do digital pre-processing before burning those 44,100 samples on the CD that you use on your high quality CD player, or that you use in a compressed form based on the MP3 standard. Yeah, maybe I should also mention this. So one of my PhD students, actually Peter Balach, who is the boss of the institute, the Acoustic Research Institute, so that's where this program is coming from, was studying the MP3 compression mode. And essentially, I would say the MP3 compression is doing the following. You create a spectrogram, but then you look at the very small amplitudes in between the high peaks, and you would say, well, what if I leave them out? And the answer is yes, you can do it, and you will have a hard time to distinguish if you do a good pre-processing, if you remove those frequencies, and because you cannot hear due to physics of the psychoacoustic phenomenon of masking, you cannot hear those little things, and therefore the idea is you can explain the idea of audio compression based on the MP3 coder via the spectrogram. So take the spectrogram, throw away information that nobody can hear because nobody can hear fine details. Even if you're a trained musician, it's very hard to make a distinction, and then you go back. So obviously I was losing a little bit my focus now, but I think I have shown you the different things, and probably it's a good time to stop now. I mean, we have to make arrangements in a practical way. So I would like to go back to this other thing, sorry. Yeah, maybe I'll leave the spectrogram running here. And start it again. Yeah, so I would like to encourage all of you to write a few lines about what you think you would like to learn from the course, maybe what your background is. So I have really I have a very vague idea of what the background is. I will not assume functional analysis, but I will use it and I will try to explain it. So for example, this idea of completion, going from simple signals to more complicated ones. I hope to address during the course also the question of, what would be a more detailed mathematical explanation of things that you have seen in the introductory courses. How can you go from continuous signals to the sampling process? So either practically using MATLAB or theoretically using certain function spaces or so. And yeah, so altogether I'm looking forward to a nice course, and I'm glad to see that so many of you have already been able to join this very first course. I have to mention that the original plan was for me to start physically in the lecture room today. Then I was told by the administration of ETH that as a guest I'm allowed to come to the building or enter the building only October 1st. But now with the current situation, we decided to start with the Zoom already now. And so I will see whether I'm allowed to come from Austria. I'm not living in Vienna, but outside of Vienna, whether I'm allowed without quarantine to Zurich, and so that we can meet each other at the lecture room. And then we will see how many people are in the lecture room and how we can manage it. In any way, I'm thanking you for your attention and I hope that we can meet again on Thursday at 2 p.m. local time. So now I'm trying to stop this recording and say goodbye to everybody, but maybe leaving the, I leave open. I will try to stop the recording. I will try to,